Hello everyone and welcome to episode 17 of Games with Go, where we are in the process of making a game where you can evolve crazy pictures. So last episode there was some homework. I did my homework. I added a few operations to my abstract picture tree. And if you are one of the subscribers that has access to the source code, if you get latest from GitHub, you'll get those. If not, no big deal. It might be better to use your own functions. You don't have to have exactly the same ones I do. You might get better looking results. These are the ones I added. I think all of these are new. So if you want later, you can just implement these. Most of these are obvious. This is ceiling, floor, linear interpolation, absolute value, clip limits things between -1 and 1, wraps them around between -1 and 1, fractal Brownian motion and turbulence. These two do some pretty cool effects, so might want to try them. All right, so last time we had a minor bug where when you add leaves to the tree, when you're building a random tree, we would sometimes try to add a node to a leaf node, which you can't. And so we would just try again until we finally got all the leaf nodes filled up. So that's something we need to fix. And that would be easy to fix, but we have a bigger problem related to how we're going to need to implement mutation when we start evolving our trees. So I'll try to sort of describe the problem. So imagine you had some tree. Say it started with plus, something like that. And let's say you wanted to mutate a node, and you pick a random node to mutate. So you say you want to change sign. Say you want to mutate that to plus. All right? So plus has 2 branches. Sign only has 1. So if you mutate this node, you can pull the X in, you can pull the old child node into plus, but then you have an empty one. You'll need to generate a leaf node or do something with that to fill it in, right? Maybe another X or a Y or something. Conversely, if this were a plus node to begin with, right, and it already had 2 children, and you wanted to mutate it into a sign, then you have to figure out, what do you do? Do you take the X and lose the Y, or take the Y and lose the X? And the way the code is structured right now, where we have these single nodes, double nodes, triple nodes, etc., we would have to have a separate case for every possible combination of changing from one type of node to another. So if a single node changed to a single node, we'd have to have a different code path than if a double node changed to a single node, or if a single node changed to a double node. There's many combinations, and we would have many nested if statements to sort it all out. So this is going to be no good. So we are going to refactor it, and this sort of thing happens a lot in programming. Once you do anything sufficiently complicated, there is a good chance that you will get a good way into getting it done and realize it's not going to work, and you've got to start over. So don't ever let that get you down. It's normal, happens to everyone, no matter how experienced you get. And you just have to deal with it. And go ahead and delete the code that's not going to work and try again. So that's what we're going to do. The new plan is, instead of having these different node types that have 0, 1, 2, or 3 nodes in them, we're going to have one node type that has an array of nodes. So the array of nodes will have a length, and so leaf nodes will just have an array of length 0, and single nodes will have an array of length 1, and so on. And that'll let us do the mutation logic by just looking at the length of the array, right? If we're going from from a node with 1 element in the array to one with 2 when we mutate, then we just add an extra leaf. If we're going from 2 to 1, then we just pick the first leaf or something. So you'll see how it works. So the first thing we're going to do, it's going to be sad, but we're going to delete all of this stuff from the leaf node all the way down through single node, double node, triple node. We're going to kill it. And some of this code is going to get a lot simpler too, which will be nice. And then we need to replace, well here, first let's make the new thing. We're going to call it base node, and it's going to be a struct. And it's going to have a children field, which is an array of nodes, or a slice in Go terms of nodes. And then we're also going to have a parent node. And the reason for that is when we start mutating, if we want to put this sign and swap it into here, then we need to take the parent of x and point it back over to sign. All right, so we're always going to need to know the parent nodes of every node in order to do a mutation where we swap a new node in. So with this scheme, whenever you create an operation, it's going to need to initialize this array to the correct length. And so what we're going to do is we're going to make constructors for every operation to do that. And that's going to be a little bit of boring boilerplate, but we've got to do it, so we're going to do it. And so one thing we'll need to do is replace all these triple nodes and double nodes with base nodes. So I'm going to do that with search and replace. If you're using VS Code, you can hit Control H. Type in single node, replace it with base node, and then you can click replace all or hit Control Alt Enter. That's replacing all of them. Do the same thing with double node. Triple node, leaf node. Okay, I think that's everything. All right, lots of things are going to be broken now. That's okay. So every instance of left child, we can use search and replace here. These need to be changed to reference the array. So everywhere that we've got a dot left child is going to become dot children of 0. So we'll replace everything. Everywhere that is dot middle child be dot children of, oh wait, that's actually going to be, we're going to do that. We'll have to fix some things up after. So we'll start with 1. And then dot right child, we're also going to do 1 for now, and we'll have to fix some up. Oop, right child. Okay, and then for our triple functions, we'll need to make the third one 2. So that'll be lerp and FBM and turbulence. So 2, 2, 2, 2. And then the last one, Control H again. The single nodes have dot child, and that will become children of 0. All right, so we've got all of our eval and string functions using the array now, I think properly. Good. So now we're going to go through and make constructors for all of our operations. So in Go, there is not an actual built-in support for constructors. There is just a convention. So if you want to make a constructor for a struct, you name it new and then the struct name. So new oplerp, and this will return an oplerp, pointer to an oplerp. So then we're going to just use our regular struct syntax. So we're going to do a base node The base node will start out with a nil parent. There'll be no parent to start out. But we're going to go ahead and make the array the proper size. Right, so in the case of lerp, it's a three child operation. So we give it a 3. Now I'm going to copy this. We're going to make a little template so we can go through these real fast. So the template will just be like this. This will prevent copy and paste mistakes since it won't compile like that until we fix everything up. And something to keep in mind here, if you're making a library where you have a struct that you always want created with a constructor, you can make the struct name lowercase, which means it will not be visible outside the package, and that will force someone to use the constructor to get one. They won't be able to use this syntax and do it wrong if you do it that way. Okay, and clip uses 2 children. Go ahead and close this picture. Wrap, not warp. Warp is just 1. Sign is 1. So boring boilerplate like this is the kind of thing that metaprogramming is invented for. You can sometimes automate these sorts of things. But Go doesn't do that stuff, so we don't get to do it. Okay, A10. This is the kind of thing too, if you master an editor like Vim, you probably do it really fast. Noise takes 2. FDM takes 3, 0, 1, 2. Turbulence also takes 3. Zero, 1, 2. All right, so A10.2 had a bug. Anyone in chat catch it? We were not doing the recursion. So let's fix that. Fixed. All right, and the leaf nodes have a length of 0. Almost done. All right, and this constructor idea works out well for some of these operations. Because op constant also needs a value. So we can just go ahead and do that right here, so it can't be done incorrectly. Oh. There we go, 0. All right. Missed a couple. All right, great. Now we have constructors, so we can replace all of these. Actually, we can use search and replace again here to good effect. Control H. Be sure to click right here, find in selection. Change all the ampersands to new. And then change all of the open close curly braces to open close parens, and that will change all of these to the constructor calls. That's okay. Let's fix up this one. We don't have to make the random number there anymore. Okay, great. Now we can do interesting stuff. Okay, so we deleted our old add random code, so let's redo that. And this actually gets a lot simpler, so that's nice. So this is going to be a function on base node, so all of our operations will inherit the add random function. And you pass in the node that you want to add to the tree. And we're going to get a random number to select which child branch we want to add the new node to. So we use rand int in. And we go from 0 to the length of node.children. So here's where our array is paying off for us. It doesn't matter what kind of node we are. We just see how big is the children array, and we pick a random number that will pick one of those elements in the array randomly. So if later we made a new function that needed 5 branches, it would just work. Okay, then we see if the child is currently nil. If it is, then we set node to add equal to that child. Now, something else we're going to want to do is we're going to want to set the parent of node to add equal to node. And so to do that, we're going to need a set parent function. In our node interface. So we'll need to implement it. for base node. This will be parent. Then we can just say node.parent equals parent. Easy enough. And then we can say the node that we're adding, set its parent to the node. Why aren't we happy? Oh. Okay. It's just complaining because it doesn't think that base node is a node yet. And that's because we haven't implemented eval and string. So let's do that real quick. So these shouldn't ever get called. So we'll panic if they do, so that we'll know we have a bug right away. And that's a really good practice that helped us out yesterday to find that bug with adding random nodes. You don't want your errors to be silent because they can be there for a long time before you know about them if they are. All right. Let's get rid of this for now. We're not going to use the same node counts. Okay, so now base node is a node and it's happy. All right, so if the child is not nil, then we just want to call we will use the magic of recursion and pass it on down the tree. Okay, so that's it. So add random now is a lot simpler than it was, and it works on any kind of node we give it to. We don't have to implement it multiple times. That is wonderful. Now, to solve the problem we had yesterday about adding leaf nodes to the tree, we're going to use a separate function for adding leaf nodes. That instead of picking a random branch, we'll go through the tree in order and find the spots to put the leaves. We'll call this add to leaf. We'll just call this leaf. Add it to our interface. Let's call this parent. All right, so for adding leaves, we basically want to look for the nil children and fill them in with leaves. So we're going to go loop through all of the current node's children. And if the child is nil, then we're going to be done. Okay, we're going to say node.children of I equals leaf. And we'll set the parent of the leaf to node. And add leaf is going to need to return a Boolean because this is going to have to backtrack sometimes. Sometimes it's going to go down the tree. Use my mouse. Right, it's looking for nil pointers. So sometimes it's going to go down the tree, it's going to go down here, it's going to go down here, it'll find out, oh, I can't add anything here. This is the end, so it's going to have to go back up and then look again. So we're going to have a Boolean we can return to say whether we successfully added the leaf node or not. So in this case, we will say true. We've successfully added a leaf node. Okay, otherwise, we're going to go to visit the child node and use recursion and call add leaf on that. Right, passing the same leaf down the tree. And if that returns true, then we return true as well. So if you get down the tree recursively, you successfully add a leaf, then everything bubbles back up, keeps returning true. If it's unable to ever find a leaf to add it to, if it finds no children it can add to on this node, then we return false. Oh, we need to make add leaf return bool in the interface too. Okay, so now we have an add leaf that will backtrack and find a nil spot to stick the leaf in. And if it can't find one at all, then this will return false. So we'll know we're done filling up a tree. Okay, next thing we need, we're going to need a function to count how many nodes are in the tree. So we're going to call that node count. It'll just return an int. And again, we only have to implement this for the base node, and everything else will inherit it. And this becomes really simple. We can start the count out equal to 1, which represents the node we're at right now. Then we visit all of our children. And we add the child's node count to our count and return it. Super easy. And we're going to use this when we want to mutate a random node in a tree. We can get the count, pick a random number between, pick a random number between 0 and the node count, and that'll give us a number we can use to pick a node out of the tree to mutate. And so to do that, we're going to need another function to get the nth node out of a tree, right? So if this were the tree, we would think of this as node 1, then node 2, then node 3, then node 4. So if we said we wanted node 3, we would want to go through the tree, counting up as we go, 1, 2, 3, and return that one, for instance. So we're going to make a func get nth node. We're going to pass in the tree we want to find it in. We're not going to use the receiver syntax for this because we need to, I'll explain why, but we need to operate on actual nodes, not base nodes for this. In will be the nth we're looking for, and then count will be something we'll use this to keep track of what our current count is until we get up to n. And then we're going to return a node and an int, which we're going to use to update our count when we go through this recursively. So this is pretty tricky, so I'll try to explain as I go. So if n equals count, then we have arrived, and we just return the current node and the current count. Okay, otherwise, we're going to set up an empty node result. And we're going to loop through all of our children. Oh, so we're going to need another function here. And get children. Going to return array of nodes. So when we're working with the interface, we don't have the ability to access .children like we do when we're working with a base node. So we need to make a function to do it. And then we can implement that. For base node. And that just returns node.children, very easy. I'm going to move that down here with the other receiver methods. All right, cool. All right, so that lets us iterate through the node's children. And each step of the way, we're going to increment our current count. And then we're going to get the nth node of that child and pass the current count. Right, so this count will get incremented more recursively as it goes down the tree. So it's going to keep counting up. Now, if the result is not nil, that means that we arrived at the nth node in there. So we'll bubble it up, which will result in it getting returned all the way up the stack. And if we never find the nth node, we can return null. Right, that would be if you passed in a number bigger than the length of the tree, then it was no good. Maybe we should panic here. Maybe we should panic, say like, tried to get a node that doesn't exist. All right. Do we have all the tools we need for mutate? One more thing we'll need for mutate is get parent. Set parent and get parent, just like we have get children. Very simple. And now I think we can write the mutate function. So mutate as well is going to operate just on the node interface, not on the base node. Okay, this will be a little tricky again. So one thing we're going to need is we're going to need to get a, we'll want to get a random node misspelled that. Okay. Need to get a random node to mutate the node we're going to mutate into. And we want those to be potentially either regular nodes or leaf nodes. So we're going to pick one of all of these as one big group, rather than just picking a regular node or a leaf node. And it looks like op turbulence is misspelled too. Yep. Okay. So back to mutate. So there are 23 total types of nodes right now. And we'll make a blank mutated node. And so there are 19 different non-leaf nodes. So we'll say if the random number is less than that, mutated node equals get random node, else. All right, so at this point, we have the we have the new node that we're going to swap in to our tree. We're going to replace node with it. Actually, we're not going to do receiver. It's going to be like this. Okay, now we're going to check the parent of the node we want to mutate and see if it's nil or not. Because if it's the root of the tree, it will have no parent, right? Like plus here has no parent. But if it does have a parent, then we need to adjust the parent's children, or the parent's child, to point to the mutated node instead of the old node. So we're going to iterate over the parent's children. And if the parent child equals node, then we found the spot in the parent's children array to modify. And we set it equal to the new mutated node, right? So if we were modifying minus, we'd be looking up at plus, looking through its children, finding the child that points to us, and changing that to the new node, right? Say if we were making it multiply, then we're pointing that child over there and getting rid of that child. And that's pretty complicated, so it deserves a comment. Okay, next thing we need to do is take the children from the old node and put them into the new node. So we're going to iterate over the current node's children, the one that's getting replaced. And we'll check to see if the new node does not have as many children spots as the old node. We check for that and break out of the loop, right? So if the current node has 3 and the new node only has 2, we'll go through here twice and then stop trying to add children. So children will get dropped when that happens, but that's fine. It's a mutation, bad things happen, right? But if we do still have spots for children, then we set the child of the mutated node equal to the old child of the old node. And we have to take that child and set its parent equal to the new mutated node. Okay, so add children from the old node to the new mutated node. Then, final step. It's possible that this hasn't filled up all the spots in our new node. If we went from a 1-branch node to a 2-branch node, for instance, we'd have some nil pointers. So we want to add some random leaves in case that is true. So we'll go through all of the children in the mutated node. This should be a mutated node. And if the child is nil, then we'll get a random leaf. And we'll set the parent of that leaf equal to the mutated node. And set the child equal to that leaf. Then the final thing we need to do, set the mutated node's parent to the old node's parent. And then we're going to return the mutated node. All right, bunch of work, but we're almost there now. We're almost there where we can go, this should not be is equal because we already defined it. Okay, now we can hop over to the evolving pictures code. And we're going to start building this out to start doing some evolution. Tonight we're just going to get mutation working, but it's a start. All right, we're going to make a new struct called the picture, which will have the red, green, and blue nodes. We're going to make some quick functions on that. Just a quick string method. /n means new line. That'll like put the next text on a new line. I think that's it. So this will print out the 3 nodes of the picture, the red, green, and blue nodes. And we'll do a constructor. And for that, we're just going to take this code we had here. Okay, so the old ad hoc code we had for making our pictures, we're going to put into a constructor. So we'll say p in picture and p.r, p.g, p.b. Okay, so this builds up the random nodes. Then we need to add the leaf nodes, and that gets really simple now. We can say for and that's it. That's all we have to do, because that's going to keep adding leaves until this no longer returns true, and it will return false once it can't find any place to put a leaf. So that is much simpler than before, and it doesn't waste time like it did before. Then we'll return our picture. All right, finally, we'll have a function to mutate the picture. So first we're going to pick a which node we're going to mutate, red, green, or blue. So we'll have an uninitialized node to mutate. You know, it might have been better to have R, G, and B be an array. We might change that later. All right, now we need to know how big the tree is. So we're going to use our node count method. So we know how many nodes there are in there. So we'll get a new random number between 0 and that count. That'll be the node we're going to grab. So we can use our get nth node to go down the tree and find the nth node. We'll set node to mutate equal to that. Then we're going to mutate it. All right, now this is our this is the now mutated node, and the reason we need this is because if the node to mutate happens to be the root of red, green, or blue, we're going to need to actually update the pointers in our picture struct. So we're going to look at this, right, the node we found, and if it's equal to the top level node, p.r, then we're going to say p.r equals the mutation. Else if p.g. Again, I think if we'd used an array, this would just be a little loop. Okay, I think that's it. We can delete the old leaf adding code. And then let's go up to apt to texture. This will now take a picture, pointer to a picture. Pick. All right, so we're gonna get a new picture, pass that in. Let's see if it runs. All right, spectacular. We're back to working with random trees. Now, let's see if we can mutate it. So I'm going to set up a little mouse button event to check it. So we'll do this similar to how, where did we do this before? The balloons. Oh yeah, we left this code in here. It was just commented out. So let's uncomment the mouse state code. So we have current mouse state and previous mouse state. We're just getting the current mouse state here. Uncomment this, so we reset the previous mouse state at the end of each frame. And we're going to say if the previous mouse state dot left button if that was pressed, and current mouse state dot left button is not pressed, so you've pressed and released it, then we want to take our picture, mutate it, Then we want to update our texture. Give it a width and height. And the renderer. Okay, so we mutate our tree, update the texture. Make this win width and win height also. So we should be able to click and mutate just one node at a time at this point. All right, we have a bug. Let's see where it's blowing up. Okay, we tried to get a node that doesn't exist. So let's go up to mutate. Let's print out some stuff. So we'll have a count that we got, the random number we picked. Okay, we got a count of 21. Let's actually print our texture too. I'm also going to comment out the random seed so we'll have repeatable test. Okay, good. Get the same error. Okay, so we tried to get the 9th node and it's saying it can't find it. Okay, I think this is wrong. This is just means that we didn't find it at this step in the recursion. So I think we just return nil and a count. Yeah. Yep. There we go. So we can click. It's just changing one node at a time. And you can see what changes down here. So sometimes the changes are really small, like that one just changed a few lines. There we go. That's kind of fun. It's getting weird. All right, I'm going to make one quick change. So let's go back to the constructor for pictures. Let's make these a little smaller for now. Just so we can mutate faster. All right, so we have mutation now, which is one of the two things we need to do a proper genetic algorithm. The next one we're going to need is doing crossover. So that will mean if we have two pictures we decided we liked, say something like this, and another one like this. We could do things like pick a random node from one tree in the population of our pictures and a node from another, and then swap them. All right? So we like the way the noise looks, we like the way the sign of X looks. Now we're going to get a new tree that does noise of X and sign of X. And so maybe that'll look even better. At least that's the hope. Okay, so we'll be drawing a bunch of pictures, doing a few mutations on them, and then taking the ones we like and crossbreeding them like this to make new ones. And we'll get to go through iteration after iteration and see what we get. All right, tonight was a lot of hard work in deleting stuff, but it paid off because we can mutate things now. Any questions about tonight's stream or previous streams or comments? I'll hang around for a while making cool pictures. And mutating them. Oh, I need to change the random seed back on. All right, everybody. Good night, and I'll see you Sunday.